devices, etc. So you can ask queries regarding to which instruments to use, which are the available instruments in the industries, which are the options, etc. So that is one thing. And other thing that this session will cover mainly will be solutions to solutions in electric mobility. So it will include almost everything. So you can raise queries regarding this kind of concepts rather than going with very typical what we say this technical things. You can go with your queries which are regarding to solutions for these technical problems. Am I right, Nitin sir?
Yeah, absolutely. So we'll make. I have some presentation slides with me, but I would definitely prefer if you have the specific queries related to the electric vehicle test and measurement system. That may be from any of the component from electric vehicles. So I would be happy to answer that. Yeah, that's the crux of the whole discussion on this. Because presentation, anyway, presentation I'll be sharing with all of you on your email. So presentation you can always watch, we can always discuss, but it's always better to discuss person questions, what you have in your mind related to converters or batteries, protocols, EMI, in electric vehicles, charging system measurements. So you can ask all of those questions in this session. So I'll be
Yeah,
happy to answer.
yeah, I think participants, as I had noticed, participants did had certain questions like this regarding maybe testing, maybe regarding the protocols, maybe such kind of things. So I think this session for the participants will be perfect to raise their questions and get answers, because I think you are the person who is actually working in the industry, maybe working with this kind of instruments, test and measurement instruments, with the protocols and other things, maybe providing solutions to clients. So I think this session participants will be perfect for you to raise your queries and ask questions regarding such problems. So I think it's already 12:49, and let me just check how many participants we do have here. I think we have around 60 participants already joined. So, yeah, Nitin sir, I think we can start our session, because the next session we have after you is an international speaker. So we'll have to be very concise with the timings there. Yeah.
So
So let
I
us.
guess the time allotted for my session is for 2 hours.
Yeah,
Okay,
it's for two
perfect.
hours. So
Yeah.
you can, yeah, you finish up your session as your presentation everything is over, and I think we can dedicate some time for question hours as well, question answers
Absolutely.
as well.
Yeah, that's the
Yeah,
plan.
so it will count up properly. So Nitin sir, I
Yes,
hand over the
I am
session to
all
you.
set, sir. So I'm all set. So whenever you feel
Yeah,
we start, I'm good to go.
I think you can start the session now. I hand over the session to you. Okay,
Okay.
sir. Okay,
So
please.
hi everyone, my name is Nitin Nigam. I am the application engineer for Tektronix India in power solution basically. I have been working in power domain for almost like 5 6 years with a bigger organization who are working as an OEM on electric vehicles or the automotive industry or the power industry. To be named some of them. I have been a part of the team who are actually designing the protocols and uh, basically the powertrain modules for electric vehicles uh, from the government side discussions or from the private industries. So in this session, possibly I'll take you through the end-to-end e-mobility solution, right from the scratch, what exactly the electric architecture of a vehicle looks like, to the complete solution that can be incorporated right from the design team to the production, how exactly the things happen. And we will talk about the test and measurement part of it, how exactly the testing happens at different stages. So feel free to ask this question. From here, I'll just switch on to my presentation. Just stop me wherever you feel you need to ask the questions. Okay. Is Can somebody confirm if my slide set is visible to all of you?
It is
Yes,
visible.
sir. Okay, perfect. So this is the topic of this session, understanding end-to-end solution for electric vehicles. We will talk majorly on this. The agenda for the next, I'll try to take this session for 1 hour 30 minutes, and the last uh, 10 to 15 minutes we'll try to keep it for questions. But still, if at any point of time you have some slide questions on any of these slide, just stop me there and please drop your question over there, so I'll be able to answer it. I'll, I'll talk a little bit about the market overview, how power electronics is dominating in the electric vehicle market space. We'll talk about the internal architecture of EV. From now, I'll refer to as an EV, electric vehicle. What is the internal architecture? What are the six key application areas of EV? When you go on to the actual hardware design of an EV, what are the six major applications? So the six applications I have discussed, derived, and this is all my experience with different industries who are actually working into the EV. This is for four wheelers. A very similar would be on the two wheeler side of space also. So these we have incorporated the six application areas which are majorly as a part of an EV structure. What is the complete EV test and measurement solution? As I belong to Tektronix, I work for Tektronix. So as a Tektronix, what is the complete EV test and measurement solution that you can incorporate when you are doing into the design or validation or qualification of the EV systems? And then we will summarize the whole discussion over there. Okay. So power industry, if you look at the power industry broadly, there are few of the trends which are shaping the whole industry. Whether we talk about industrial trends, whether we talk about the automotive, data center, milga or consumer market, but the overall the hottest power electronic trends are basically lies into the power electronics, which are the faster switching power converters. You all must be aware of that the new power devices, the gallium nitride or silicon carbide, has been the hottest trend in the power electronics. Power integrity is one of it. Power integrity, how your power circuit designs are correlated with the other domains. Wide band gap semi characterization, those are basically the power semiconductors, and the battery management. So what is the new chemistry and what is the BMS system? So this all are the different power electronics trends which are happening right now in the industry. What we see from the industry in different applications, whether they are medical electronics, whether they are automotive, whether they are IoT, whether they are consumer electronics, military and government, whether there is a data center. So this is how the industry is shaping at different stages. Okay. Some of the recent trend. So this is for your reference. If you wanted to see, you just need to go onto the slide sets. Aerospace and defense. What are the new trends? What are the new trends in automotive? What are new trends in industrial lighting or consumer? So how the different industries are shaping on the power electronics domain. So just for your reference, if you wanted to go through. Okay, from here on, we'll talk only of the electric vehicles. So electric vehicle is typically into three different type of domains. One is BEV, PHEV, and HEV. One is battery electric vehicles, so which are completely based on the batteries. There is no gasoline engine into it. It's only based on the rechargeable batteries. The second category is a plug-in hybrid electric vehicles. So they have a recharge batteries and they have standard gasoline engine turns on. So that's a hybrid electric vehicles. One is a hybrid electric vehicles which are powered by both gasoline and electricity. They have their own braking system which is known as a regenerative process. So the categories of the electric vehicles is being defined into three different domains by the industry. Similarly, the chargers are defined into three different type of chargers. One is the level 1 charger, level 2 chargers, and level 3 chargers. So depending upon the type of capacity that charger can charge in that amount of time, for an electric vehicle which can run for the duration of the time, that level of charges has been defined. So level 1 takes almost an 8 hours, level 2 takes almost 4 hours, and level 3, the new chargers which are coming up, they can charge approximately in 30 minutes up to 90 miles range. So this is how exactly the charger markets are defined on. So if you look at the some of the few examples of it is if you talk about Tesla has recently launched a new electric vehicle with a charging capacity of 15 minutes. So those are basically the gallium nitride based EV chargers which have been launched by them, and it's like more faster EV charging systems that has been designed by them. some of the key examples how industry defines the different type of chargers. If we go deeply into the architecture of an electric vehicle, right, left, exactly from, if you look at the AC input side, so there are two types of inputs into the electric vehicle. One is an AC input. So this AC input goes into an onboard charger, which is OBC. We call this AC DC converter typically. So there is an AC input charger outside, or there is a DC input. So that's a direct DC which feeds into a DC and it goes directly into the high voltage battery. So there are two types of charging systems. So AC input and DC input. AC input goes into onboard charger, which is nothing but this is just an AC to DC converter. After this DC gets converted, this is a bus bar, then there is a battery. Battery is connected to an inverter, and inverter is further connected to a three-phase motor, and the motor is connected to the electric wheels of the particular car. In order to get connected, there are different type of protocols which are running into it. So there is a CAN protocol, then there is a different DC converter which runs onto the backside 12-volt battery which works with different ECUs. These ECUs are talking to each other based on the different protocols. If you look into the more broader architecture of it, this is again a AC/DC converter. Then the green bars are basically the protocols. Then we have different type of converter topologies into it. There is a battery management unit, which is basically the battery management system. We have different type of motors, hydraulics, which are being controlled by the system on the ECUs. These ECUs are together connecting with different protocols. And then there is the mechanical electric vehicles which wheels which are basically connected to the motors. So if you look at it overall architecture of it, so we have summarized into a very, this is a more broader, simpler diagram. Two types of inputs. One is an AC input or DC. Then if AC, then it goes into onboard charger. If it is DC, it goes to a DC battery. DC battery then drives a DC-DC converter and the motor drives. Or there are different type of converters for different topologies, and this motor is then connected to wheels. So the whole idea of the power electronic system is basically AC/DC charging station, onboard charger, and the EV batteries. So are three major broader areas of application, but we have segregated them into a six major border so that we exactly know from end-to-end systems how exactly the system is working into an electric vehicle. So we have categorized them into AC charging station or DC charging station. So if you are working on AC charging station, then there is a separate application. If you are working on a different converters or inverters which are this internal AC DC converters, then there is a separate application. If you are working on the motor drive systems, there is a separate application considered. If you are working on the battery management system, it would be altogether a separate system. If you are working on the communication protocols, that would be a separate part of it. If you are working on the EMI EMC measurement, that would be a separate part of it. So overall, if you look at the whole system, then there are six applications which we have defined into this whole electric vehicle architecture. EMI EMC I have considered because there are a lot of standards. If you talk in the Indian market, then there's a lot of standards which are defined by Bureau of Indian Standard (BIS), which define the EMI EMC standard required for electric vehicle to be certified. If you talk in the communication protocols, it's not only CAN or LAN. Now the industry is shaping into the much faster protocols, which are known as the automotive Ethernet. If you talk about the battery management system, so there are different standard for battery management also, which I'll going forward. I'll talk about it. Then the motor drives can be of different types, so that's one application of it. Then there are different AC/DC converters or inverters, which helps us to run the electric vehicles, and obviously a charging station which helps to charge a particular and that we have identified in the electric vehicle. Any specific question till here? If somebody has it, he can ask. He or she can ask. Okay. Okay. uh, Basically, when we talk about an AC charging station, then there are different type of test parameters that needs to be defined for designing these type of charging stations. So as an industry, we have been doing all of these tests, which I have listed down. It might be a single phase or a three phase. I have listed down the different test items which are needs to be performed when you're doing an AC charging station. So this is basically test before power on test, open close test with loads, output power test, overcurrent protection, communication. List down the different type of tests which are being required into a AC charging station. Similarly, when we talk in terms of a DC charging station, it requires a lot of instrumentation, as I have highlighted on my slide set. You might require DC power supply, different type of electronic loads, different type of power meters, scopes, switch analyzers, simulation boards, some dedicated software. So a dedicated whole system which basically charge discharge uh, creates different condition using electronic loads, different condition using a different type of sources, power supplies. So DC charging station helps you to understand the DC properties which are being required to charge these stations properly. Okay. This is another when we go exactly into the onboard chargers, this is how the functional diagram looks like. You have an input stage, then there is a power factor correction, then there is a different DC-DC converter which is further connected to the battery management BMC. Then there are different type of power management, different type of data acquisition, and the microprocessors which are being connected using the CAN protocols. So this is a very broad architecture of an OBC which we have taken. Okay. If we go in the second application part of it, then the power electronics in electric vehicle is considered from the DC AC, AC DC, DC DC converters. So this is an overall system which you can correlate with the first diagram which I was showing you on the internal architecture. It might be a single phase or a three phase, which is further connected to a converter. Okay, then we have DC bus. This is bidirectional DC bus. Then there is an inverter which is connected, three-phase motor, and then the electronic. Then there is a load. So this load you can consider as the wheels, the motor that is being connected, which is connected to the wheels. This is driven by an inverter, which is there is a control logic, then which is connected before the DC bus, and then there is a converter. So this is a very broad overview of the diagram that I've taken for an onboard charger, so that you know exactly that when we are designing any onboard chargers, then what are the components which are internally connected into the complete system. So, what are the challenges that we face when we are designing any converter or inverter? High efficiency, everybody requires an high efficiency converters. You require applications which has peak power capabilities to handle. You need less losses, maybe in the transformers or the in the switches. You require low load power consumption, should be as less as possible. Uh, the new incorporation of the wideband gap devices, which are SiC and GaN, has also created a lot of test challenges. EMI, EMC, and the power integrity. All these test challenges, when it comes to a converter or inverter design, it becomes very important as a design engineer or as a validation engineer. It becomes very important to overcome all of these challenges, to do the testing and the debugging into these challenges. So these, how do we take care of these challenges is a very important parameter. When we design any EV, these are the design consideration. If you wanted to increase the efficiency of the whole system, you need to work on the switching technology. If you wanted to reduce the emissions, you need to work on the slew rate. You need to reduce the load reactance. If you wanted to work on the reliability of the device, you need to work on the robustness and the thermal management. If you wanted to reduce the weight and the volume, then switching technology or the topology is very important, because there are a lot of converters and inverters which are used. So choose what switching technology are you using? Are you using SI devices, or are you using SiC or GaN? That's very important. If you wanted to decrease the complexity of the whole system, the switching technology and the topologies are more important. So these are the design consideration which industry is actually working on. They consider these parameters as their consideration when they're going for a new design in electric vehicle. So efficiency, how efficient you want to design, how complex you want to design, how reliable you want to design, depends on these key parameters. So it's very important to understand that when we are designing any electric vehicle component, or when we're testing any electric vehicle component, what all the major factors we need to consider for. Okay. So now coming to you would be knowing, or you would be working on different type of converters. Somebody might be working on AC/DC, somebody might be working on DC/DC. But what are the critical measurements when we actually design that when the application? So I'm talking on the board level. So when you have actually designed a power converter and you wanted to do the test part of it, the validation part of it. So what are the critical measurements for power converters? So I've just taken an example of an AC-DC converter. Okay, so this is a very typical AC-DC converter. You might consider a DC-DC, you might consider a DC-AC, you might consider single phase, you might consider three phase, or the measurement challenges remain same. So right from the input side, we are doing some measurements. So these are very common. Most of you would be aware of it from the input side or from the output side. Okay, this is something interesting. You actually want to measure the losses across your devices. So you might want to measure the turn on losses, turn off losses, conduction losses, total losses, slew rate, IDS, dynamic on. You might want to measure the transformer losses, okay, which the transformers that you're using into your converters. You might want to see the BH curve. You might want to see the copper losses. You might want to see the magnetic properties in the core. You might want to see the inductance in the loops, inductors, okay, or you might want to see the control loop response, how your actual converter, the frequency response analysis, how your converter is stable or not. So you might want to do all of these testing at different stages. So if you're working on any converter design, so it's very important to do these testing at different stages, at the input side or the output side or the transformer sides or the switching side or from the overall stability side of the whole converter design. So these measurements are applicable for DC-DC, DC-AC, AC-DC, all different type of converter designs. So if you are working on the ground level converters, it's very important to understand all of these measurements, the importance of these measurements at different stages. So I have segregated them into different formats, right from input to output, from AC-DC to DC-DC, power stage.
Sir, mic is muted. Please turn on your mic. Sir, no audio.
Is it audible now?
Yeah, it's fine. Yes, sir. It's audible, sir.
So were you able to hear me out in the earlier slides?
Couple of seconds we were missing you. Couple of seconds we were missing you.
Oh, couple. So okay, I guess. Okay. Okay, so so we have segregated these measurements at different stages. So right from your timing switching analysis, I don't know how many of you do real switching analysis in terms of to measure the switching losses in a GAN device, or to measure switching losses into a SIC device or a SI device in a conduction state. So that's very important because it really tells you how your device is performing. Uh, how you measure the dead time between the switches. So when you're using multiple switches, how the dead time is being measured at different stages. That's very important. What is the amplitude analysis that you do? What is the magnetic analysis that you suppose you're using an inductor into your design? What is the saturation level of that inductor? How much time does it take to get saturated? What is the BH curve of that inductor? What is the losses which are happening into that inductor? So if you are able to deep dive into these measurements, you will be able to design a much better converter design. If you are able to measure the control loop analysis, control loop response, the stability of the whole converter, you would be able to know how stable your converter is in different load conditions. If you are able to measure the impedance into it, you will be able to know how your converter is going to behave under different current conditions. So similarly, from the output side, the efficiency part of it, ripple part of it, or the compliance safety testing part of it. So these are the different critical measurement that we are doing on the onboard chargers or from the AC/DC, DC/DC, or DC/AC converters. Okay. Just to show you how exactly they looks like. uh, when we are doing the power converter measurements, so similarly we are doing the input analysis which gives you the power quality. It is as good as you are doing a power quality analysis of the input side of the converter. Similarly, when we are doing in harmonics, so I'm not sure how many of you have done the harmonics as per the standards. So when we talk in terms of the electric vehicles, so there are a couple of standards which are being defined. As I have mentioned into my slide set also, so there are different type of standards. When we are doing it for DO160, so these are like airborne standards. So if you are designing a converter which has to be used in an airborne facilities, then that has to be comply with DO160. That's an international standard. Suppose if you're designing military applications on a shipboard, on a ship, then MIL 1399 is a very dedicated standard. When you're doing it for normal amplitude, AM14 is one of the standards which are used for different protocols on a defense systems. It's a kind of a standard which is used for defense systems. Then 6100 is basically for consumer electronics and the automotive industry, which majorly is being used. So doing a harmonic analysis as per the standards is a very crucial stage of characterizing any converter. It's very important to understand whether your converter is following that particular standard or not, which really helps you to get the correct limits, the tolerance limits of the harmonics of your converters at proper stage. In this current input capacitance, so these are like a regular measurements which are being done on any specific converters. Okay, this slide set is important. Switching loss measurements. This is important because this really tells you how your switching device is performing. So you can actually measure the turn on losses. You can actually measure the conduction losses. You can actually measure the turn off losses. These all losses can be analyzed in a real go situation. So when I say real go situation, I mean that when your converter is actually taking onto a load, it is actually into the design. Then how you wanted to see your switches is operating in different conditions. So what is the conduction time for that switch? What is the conduction losses? What is the turn on losses? How much time it takes to turn on? How much time it takes to turn off? So you can actually see the performance of your switch in a real life situation. Similarly, the safe operating areas is a very important parameters. We all know that when you wanted to use any component into your design, then there is a specific specifications which are defined for a component. Suppose you are using any MOSFET into your design. Those those devices are rated, when you see the data sheets of those devices are rated to work as per 25 degrees Celsius or the room temperature. But when that component goes actually into an electric vehicles or into any specific converters, they are not working on a 25 degrees Celsius. They might work on 70 degrees Celsius, they might work on 60 degrees Celsius. So there would be a different different temperature conditions, there would be different environmental condition on which they work. So this measurement is basically designed to actually know whether your device is operating in different ranges of maximum current, voltage, and power. So if your device fails in any of the three situations, you can actually predict that your device is operating into the maximum voltage and it fails. Or your device, when it is going through a maximum load, it fails at different voltage or the current levels. So it tells you a real life situation of actual converter, of actual switch which is being used into a converter. DI by dt and dV by dt, as I told you, these are the slew rate measurements, the rate of voltage and current with respect to time. This actually defines one of the key parameters when you are designing your converters. So how your voltage and current are changing with respect to time. So this is a very important measurement which people do in the industry when they wanted to see the real life situations of a switch. Okay, dynamic on resistance. So this is also a conduction measurement. So when actually this happens, when the device is actually operating. So when the device is operating, what is the dynamic on resistance for that? This measurement tells you that particular parameter. Magnetic analysis. So this is something interesting which I personally also like, and people in the industry actually follow one of the Tektronix method to do this measurement. We are actually showing you the live BH curve of a core of an inductor. So this measurement tells you the magnetic property. So whether it's permeability, whether it's BP, BR, FCH max, delta B, delta H. It tells you the inductance values. It tells you the magnetic losses into the core itself. So we have defined different algorithms across it, which tells you the different type of losses into the core itself. So this is one of a tectonics patented algorithms or a measurement that helps the designers to validate what are the losses that are happening into the core as well as into the transformers. So this is a very interesting measurement to do in the actual converter design. Okay, Ripple, most of you would be knowing about it. Ripple is one important parameters. So you wanted to check the output, the AC ripple on the output of a DC. So this is a very important ripple. The difference in the way the industry does the measurement is they might want to see the ripple which is happening because of 50 hertz, and they might also want to see the ripple which is happening because of 100 kilohertz of a switch, or maybe 1 megahertz of a switch if it is a GAN or a SIC, or maybe 40 kilohertz of a switch. So it's very important to analyze the frequency ranges of the switch. Well, how the ripple is changing with respect to the frequency. Is it because of the line power which is happening? Is it because of the switching component which is happening? So understanding the low frequency ripple and high frequency ripple is very important. I mean, this really defines, or it really defines the quality of the converter. Power efficiency, obviously, this is what is the input to output that we are getting into the design. How efficient is this? Whether it's 80% efficient, 85%, 86%. So that's the usual measurement. Okay, this is an important measurement, which is a control loop response. This power supply engineers or the designers, they rely on the Bode plot for the stability of the whole converter design. So what is the crossover frequency? What are the gain margin? What are the phase margin? This is a dedicated important measurement which which people are which I see a trend nowadays. For the last 1 year, I have been asked a lot of questions on how exactly we are doing the Bode plots. So what meeting become? Mr. Yes, uh, sir, your voice is a little feeble. Can you be a little not on mute? I guess. Yeah, sir. Can you be a little louder? I can. If you have any specific query. Okay. So if you have any specific query, you can type it in the chat window. When we end this, we'll take all of the queries which are a part of the chat window. So this is one of the important measurement on the control loop response, which is a lot of power supply engineers who are designing the converters. They rely on Bode plot for the stability. If the load changes, how the output of the power converter changes. So that's one crossover frequency, gain margin, phase margin. That's like very important three parameters that are being defined. Uh, Another important measurement into the converter is the impedance measurement, input impedance. So this happens because on the reverse recovery current that happens into the converters, in order to measure the impedance on the input side, it is a super important measurement. This is also one of the Tektronix patented algorithms that we do into our system using different power converters we have inbuilt into the platform. So this is an automated impedance measurement that's being done. Okay, this was about the converter design, but another important part of is SIC and GAN. Okay, a lot of people, a lot of research which we see across the globe. It's not just India, but we see this SIC and GAN coming up in US, China, Japan, Europe, and now India is also working on SIC and GAN. A lot of research in a lot of IITs is being going on. People have started designing converters. I see a lot of white papers, a lot of journals which talks about SIC and GAN. The application of SIC and GAN is very important in the electric vehicles, because if you wanted to reduce the size of the ECU, so if we know how many ECUs are generally a vehicle has, if you talk about normal car, so normally an ECU in a normal car, if you talk an example of a very basic car, there would be hundreds of ECUs. So if you talk in a top end car, there would be thousands of ECUs. So if you wanted to reduce the weight of the whole car. If you wanted to increase the efficiency of the whole system, whole machine, you need to reduce the size of your converters, because the converters contribute to a lot of weight into the electric vehicles. If you wanted to reduce the size of the converters, you need to switch on to the GAN and the SiC devices. They are much faster. They have much faster switching speed. They get much faster charge. Okay, so if you talk about the size and the power density, so we are shrinking it to 80% to get the most higher efficiency. So this is a Toyota SiC based battery charger. So you can imagine the from the left hand side what you see, to the right hand side what you see with respect to the GAN SiC based charger. How to get more power density? Okay, so this is an example of it. You have smaller parts, capacitor inductors. So on the left hand side, if you see, these are 200-volt silicon device. So this is a real picture which I have taken from TI, and one of our customers, I can't name, but one of our customers use these devices into their converters. So left hand side, if you see, these are 200-volt silicon device, and the smaller one that you see is a GAN device, which is the same 200-volt with 25 milliohms RDS and this 30 milliohms RDS. Similarly, if you see the GAN and the SiC based device, so the size of that is almost half of it. So we have so in order to get the higher frequencies of the switching, you have smaller capacitors and inductors. But this also comes with a lot of challenges. So we are getting there are different type of challenges that happens with GAN and C. So what are the different differences between GAN and SiC? The Miller charge QG is much lower, so which allows faster switching speed in GAN, but they require less parasitic capacitance, resistance, and inductance. The maximum VGS and maximum VTS is much lower, SiC, but they require very tight regulation of VGS and VTH voltage. So if you look at the typical gate bias voltage also onto the GAN, so it's like 0 to 3 with respect to 9 to 15, minus 9 to 15 volts. So gate bias voltage is typically very less in comparison to a GAN systems also. So you can consider that when we have uh, Miller charge, which is the Miller plateau, basically that the time is very less. So the switching speed of the GAN devices are much faster. All the SiC devices are much faster, so they are operating at a much faster switching speed. But it's not easy. So the testing parameters are very typical for GAN devices. Uh, if you are measuring on the Miller charge, which are much faster, you should have the ability to measure extremely fast dV by dt and dA by dt. You should be able to measure VGS on all gate nodes in a circuit on high side and low side when you want a tight regulation of VGS and VTH voltage. Okay, require a tight regulation of dead time to minimize losses. So you should be able to measure correctly turn on time, turn off time, dead times, phantom ringing, which is happening on the high side and the low side switches. So there is a dedicated measurements. So when we talk in terms of the GAN and SiC devices, these three measurements become very important with respect to these devices. So you need to measure the VGS on the high side and the low side. So when we are talking this side and this side, both of it, you need to measure the dead time. VGS and VDS measurement on low side and high side simultaneously. What is the dead time when one of the devices turns on, then the other turns off? So the time between the turn on and turn off is actually the dead time. So lower the dead time, faster the device, more the ringing, phantom ringing. So more the ringing, so the better system has to be used in order to measure this. Efficiency and the loss. So what is the efficiency of the device and what are the losses that are happening into the GAN devices? Okay. Why is dead time optimization important? So as you can see, as I told you, uh, that time is important because if your devices is turning on and turning off, the time between two devices is much smaller. Your device is operating in a much faster frequency. You're switching much faster, so that's why the dead time is very important. The picture that you see right now on the screen, showing you one channel is going down, the yellow, and the blue channel is going up, and we are trying to measure the Miller plateau into this. So this Miller plateau is connected on this green one that you see is connected on a VGS node. So on the high side, so you can easily imagine this point that is marked is a Miller plateau point. but the lot of ringing that happens, so this ringing can't actually tell you when the device is turning on. So if you don't know the turn on time properly, you might not be able to calculate the turn off time. Your conduction time will be much smaller, much higher. uh, if your conduction time is much higher and your device capabilities are much better, then you are actually not taking the full utilization of your GAN or the SiC devices. So dead time optimization is very, very, very important. So how do you do these measurements? Generally, these measurements are being done on a differential probe. So there are a lot of questions that are being asked. Are these measurements can be done on using a differential probe? Do they have a required bandwidth? Do they have a required voltage ratings? Do they have a required floating voltage ratings? Do they have the enough low inductance or the enough low capacitance? The answer is traditional answer is no. So you can't do a measurement on a GAN and an SiC based devices using a normal differential probes. So what really happens? So the one that you see on the left hand side is the yellow image is basically a simulated results on the oscilloscope. But the one that you see on a purple waveform, that's the actual signal which is being captured. So the result does not match. So you'll not be able to really measure the turn on. You'll not be able to measure the Miller plateau. You'll not be able to measure the dead time. You'll not be able to measure the conduction time. It becomes almost impossible on a GAN and SiC based device to measure these parameters. Okay. The problem is the common mode rejection ratio. The common mode rejection ratios are very, very poor over normal differential probes. So it requires some specialized solution to get this problem sorted out. So that's altogether a different topic. So I'll not go into the product based, but these are separate systems, optical systems, which are used in power electronics for doing these measurements. So there is a separate system for that. I'll not go into the portion of that. Another measurement is a motor drive analysis. Motor drive analysis is a very, very important measurement that a lot of people does. So this motor drive analysis basically uh, is the next stage with respect to the converters or inverters. So you remember the first diagram, we had the inverter which is connected to a three-phase motor drive. So what are the motor drive measurements? So if you are using any of the BLDC, induction, PMSM, universal stepper motors, which are used in different electronics devices, they might be chosen upon the type of applications. So as you can see, if you're talking about the BLDC motors, they are high efficient, they have high dynamic response. If you're choosing an induction motor, they have low cost, they are more robust. If you're using a permanent magnet, so they have low rotor inertia, higher torque and better performance. Depending upon the type of the application, the motors are chosen. The drives are chosen depending upon the applications. Okay. But the measurement that are very, very important to motor drives are the three-phase measurements of the motor. So when you wanted to measure the three-phase power quality, where we are seeing the phase one, phase two, phase three, the different three-phase measurements. Uh, so you can do the different type of wirings basically into the system. Okay. Okay, now here again the harmonic analysis comes. So when we were talking on the harmonics on the converters, we were talking on a single phase with respect to a particular standard. When we are talking on the harmonics on the motor drives, then also we are talking of the standard. So IEEE 61000 is one of the very, very useful standard, and IEEE 519. So these are the two standards which are used by the motor drive analysis. So these are international standards which defines your pass and fail status when you're using the motor into your design. So if you wanted to characterize the motor efficiency and the motor electrical parameters, how it is operating into different load conditions, then it becomes very important to measure these as per the standards. Another is an output analysis, which is the measuring the overall efficiency of the whole system. So efficiency is basically testing how efficient your motor is in different load conditions. You can actually define that and you can measure that into the system. Okay. Then there's the phasor diagrams, which basically tells you the lead and lag of voltage and current. Okay. Ripple analysis on the motor on the three-phase systems. Okay. So you perform all of these measurements related to the phasor diagrams or the three-phase analysis in terms of the waveforms, measurements, and the harmonics chart. So overall, you get a complete picture of the motor drives. We have also other measurements measurements which are onto into our platform, which we are talking, which we can, which define the torque and speed of the motors. So they are not covered into this presentation, but yes, we can talk separately if somebody wants to talk on that terms also. So these are all electrical part of it. Apart from that, the third application, which is another important measurement, is the battery management system. So BMS is considered, so battery management system is considered as a part of the battery pack. It is basically a different type of cells which are combined together to form a pack. So what exactly is there into a battery pack system? So you have a battery pack, then there's, so it's basically a module. Module has different type of cells. So the testing is being done at the cell level. The testing is done at the module level or at the complete battery management system. So when we talk in terms of the battery management system, so we talk in terms of the cell level testing, module level testing, or the pack level testing. Okay, there are typical different type of. I have taken an example of a technical specification of a cell of a BMS system. So this is a complete BMS system which defines cell. What is the cell voltage? What are the number of channels? What is the cell temperature? What is the pack voltage? What is the pack current? So this is from the cell level. This is from the pack level. This is the external interface of the battery drive system. What are the different type of digital inputs? Analog inputs, temperature channels, digital channels, and what is the communication, how the battery management system is communicating with the other devices. Now the BMS has also come up with the different type of connectivities. This slide said mention CAN, but now they have also come up with an automotive Ethernet. So this is how a whole system of the BMS looks like. So there are different type of test packages from cell to level. So the application that covers when we talk in terms of the battery is battery charge and discharge, performance test, battery cycle life test, battery capacity test, quality check, and the production testing. And this is also different type of ATs that are being formed to do all of these measurements. So if you are looking onto a application where we wanted to measure the battery management system, you might want to do the battery charge and discharge test. You might want to do the performance test. You might want to do the battery's life cycle test. All of these tests are different conditions. So you might want to test the different batteries, maybe lead acid, nickel hydrogen, lithium ion, supercapacitor. The applications are battery capacity test, internal resistance test, battery temperature measurements, battery charge and discharge. There are different type of cutoff conditions and different type of safe conditions. When we say cutoff conditions, I mean that you might want to measure the time for the charge, the voltage, capacity, energy, OPP, over power production, voltage fluctuations, cell voltage, cell temperatures, CAN messages, how is this connecting or communicating with the other devices. So there are different conditions, there are different applications, different type of batteries that can be tested, and different conditions and the safe conditions which are being required. Okay. Uh, so this is the battery management function. So there's in industry we use the DBC files. So DBC files are basically the files which tell us a lot about the BMS systems. It tells a lot of conditions which needs to be tested into the battery. So this is an automated file which actually runs into a DBC system and tell us a lot about the automated battery management system setups. Okay. Very important is a driving cycle test. So if you want to test the simulation of vehicle driving, acceleration, de-acceleration, climbing, braking with 1 million points, positive or negative. So that's basically a drive cycle test which is being done. Okay, so this is an overall test summary. If we talk in terms of the battery life cycle test, capacity test, no load system on chip test, overcharge and over discharge rate, endurance test, high pulse test. So these are all of the tests which are required when we are working on a management system. Another application that comes into picture is the communication protocols. Okay, communication protocols are another important parameter which are being required in a complete electric vehicle as an overall architecture. Uh, so there are different type of protocols. So it might be a Zigbee protocol, it might be an RS-232 protocol, it might be a USB Ethernet protocols. When we talk in terms of the battery chargers, the communication happens through CAN bus protocols. The communication happens through Ethernet protocols. When we talk on the battery management system, there are different protocols. If you talk on the display, then there's an I2C, SPI 485, CAN bus, and the Zigbee protocol. So the protocols are a very play a very very important architecture into the whole electric vehicles. Uh, Depending upon the speed, the cable type, the cost, and the application into the electric vehicles. So on a overall vehicle architecture, if you're talking on the 1 Mbps, if you're talking on 19 Mbps, if you're talking on 10 Mbps, 23 Mbps, and if you're talking on the Gbps, how fast the communication is happening on an electric vehicle, that's where it defines how you're defining the different application, ABS, powertrain, engine control. So these are the different application areas which uses different protocols. So you need to understand the automotive serial protocols in detail in order to get the complete architecture of the communication in the complete vehicle architecture. So right from CAN FD to LIN, FlexRay, USB, automotive Ethernet, RS-232 most. So you need to understand exactly how your complete architecture of the complete system in a automotive works in the protocol level. Okay, another sixth application is EMI/EMC. So it's one of the most important applications. We do four level of phenomena: conducted low frequency phenomena, radiated low frequency field phenomena, conducted high frequency phenomena, radiated high frequency phenomena. So if you look on the right hand side of the diagram, then you would be clearly seeing what are the different flickers that happens in different stages, or what are the emission that happens across the motor drive when we are connecting with the inverter. What happens when there is a device which is connected across the BMS system, or what happens when the high frequency inverter noise, low frequency magnetic field, power magnetics, sensitivity cell and cell monitoring electronics. So across the BMS, across the inverters. So there is a lot of emission, EMI, EMC emission that happens in a car. Okay. So the requirement for EMI/EMC is a CISPR 25. CISPR 25 is one of the standard which actually defines for automotive industry. So they have different standards. They have different CISPR limits. So CISPR is basically a universal body for EMI/EMC standards. So they have different standards on EMI/EMC. So the primary purpose of CISPR 25 testing is to ensure that the component to be installed in the automotive will not interfere with other system within the vehicle. So how do we are doing? How it is being done? It is being done through different type of softwares, hardwares, antennas, tripods, preamplifiers. So there are different requirements for EMI/EMC altogether. So if you look at the complete test requirements on the electric vehicle or from the automotive side, there would be scopes that would be required. There would be software, there would be electronic loads, AC power sources, integrated system on the BMS side, or the spectrum analyzers with required software. Okay. Then there are different conditional accessories which are also being used. So these conditional accessories will tell you these are basically the sensors, the data loggers, the fixtures, the for protection which are being used in the automotive industry. So if you look at the overall trend from the okay, this is my slide set which I have used for to explain the automotive trend, how power electronics is working into different domain. Okay. So any specific question over here, I'll pull up another slide set just to show you what different how we are doing it for different industries on the automotive side.
Sir, am I audible?
Yes, you are audible. Please go ahead.
What kind of specific care is required to be taken when we do test and measurement for the GAN devices based board, which you demonstrated? Any
Okay.
specific care we need to take when we do the measurements for the GAN devices?
Yeah, I am just coming to it. Yes, I'll open that. So your question is, I'll just open it. Just a second. Maybe. Just let me know, sir, when you are able to see my slide set.
Yeah, it's visible now.
Yes, sir.
Okay. Okay. So what really happens is, uh, okay, this slides I showed you where you see this yellow channel versus the purple channel. So yellow, what we have done is it's a simulated results of a in a MATLAB, and we were trying to simulate a device and characterize the VGS side of it, and we could see that the it's a very plain Miller plateau. The one that you see Miller plateau, that's the Miller. So that's the time for the device to get charged, and then the turn on time starts. But in the purple one, you don't see that. Okay, why this really happens? This really happens because of the common mode rejection ratio. Okay, so when you are using a normal differential probe, the devices have a very poor common mode rejection ratio. At 100 megahertz, it's like 26 dB common mode rejection ratio on a normal differential probe, and that is in any differential probe in the industry. So when we are talking, so GAN devices requires more better common mode rejection ratios. So if you look at this slides, I'll just pull up this one. Okay. So this is so there is a specialized method that Tektronix is doing. They're using an IsoView probe, okay, which is Tektronix IsoView probe for doing these measurement on the SiC based converters, which is 1 million is to 1 at 100 megahertz. So you just compare when we are talking on the common mode reaction ratio of 26 dB at 100 megahertz versus 1 million is to 1 at 100 megahertz. So because of the architecture of this probe, completely isolated. There is no electrical path into this probe. We are using a separate optical converters. So if you look at this, this is the probe tip. Then we have electrical to optical converter. Then there is an optical to electrical converter, and then it goes into the oscilloscope. So the tip which actually touches your VGS device uh, shows you the connectivity in terms of the electrical, but as soon as you touches it, it converts into a optical signal, and then it transfer onto the optical fiber. So this whole testing which is being done does not introduce any inductance which is created by the electrical path of the probe itself. So it becomes very easier for user to characterize the turn on and the turn off of the GAN and the SiC based devices. It's a very I would say easy approach, because when you are using a differential probe, the complete electrical length of the probe creates a lot of noise into the switch itself. When as soon as you connect it with the switch, it creates a lot of noise. But since we are using an optical method to measure this, the noise is comparatively very less.
Okay, sir. May I ask you the cost of this tool?
Cost, I'm not sure, sir. I mean, like, I can connect you to the concerned person for this. I had also tried to get one paper which I think would be very useful for this, the whole team. Let me just open that paper. And this paper can actually be very helpful for anybody who is working on the SiC based converter. I got that paper today morning. Somebody shared that paper, and possibly I'll share that paper with the whole team also, so that uh, I don't have an IEEE access, but I'm sure a lot of people in this group would be having an IEEE access. So they can actually download that paper, and they can have a good study on that. So is it visible now?
Yes, sir.
Okay.
Yeah, it is
So
visible. Doing a
yeah this
validation of SiC power.
Yeah, this paper name is Modeling and Validation of SiC Power Modules. You probably can download this paper, and this talks about IGBTs and SI MOSFETs, SiC based MOSFETs. This talks about the different type of VGS measurements, and if you look at the experimental setup over here, I don't know if that picture is completely visible to you or not, but yeah. So this uses an IsoView optical probe for VGS measurement. Is it visible to everybody? Hello.
Yes, sir. Yes, sir.
Yeah.
Yes, it is
So
visible.
yeah, this paper talks about this IsoView optical probe for VGS measurements. So this is this is a very, very interesting paper. I have just got the abstract. I'll try to get this paper from IEEE. I'll purchase this paper. But yes, this paper talks a lot about doing these measurement using an optically isolated probe on the SiC based devices. And the results are very beautiful. If you look at the results on the top bottom side, the results are very, very interesting. So if you look at the screenshot of the oscilloscopes, so you look at the VGS side, yeah, this yellow one, and where the device goes down, and you see the current also where the current gets up. So you can actually measure the turn on, turn off. Very interesting results on
Okay,
the
so what is the
oscilloscope.
switching frequency here in this case?
Pardon?
What is the switching frequency in this case? Can you just tell me because I'm unable to check that.
I am, sir. I don't have the exact. So let me just look at the.
Just check whether it is available in that.
Yeah, it should be available in the paper somewhere. I just got this today morning, so I thought that I'll share it with the team so that people who are
Yeah,
working on this.
yeah, because while I was working in my MTech, in my research work, I had used this. I was working at a frequency of 200 kilohertz. So in there, I had received, I mean, the results were not that much clear, though I had used this Tektronix differential probes itself.
So
But
differential
still,
probe. So
the high
that's
frequency was not clear. So this may be helpful to me as well.
so,
That's why I
so
was
the
asking.
problem with the differential probe is that the CMMR ratio, which I was showing in the slide set, when you talk in terms of the common mode reaction ratio, the differential probes have a very poor CMMR ratio. That's where the whole picture comes. So, so if you can correlate your result, then you would be seeing a lot of ringing on your measurements.
Yeah, that's what I saw because these results were very clear. In my
Yes,
measurement, I had got much of this ringing, which was actually not there in the device itself. I mean, in
absolutely.
the
So
device of
that's
the converter, but on the I mean, on the oscilloscope, I was getting much of this ringing.
absolutely, sir. Yeah. So that's what the whole system. Drain current is like TMN. So I don't see the part number of it, but you can actually get this paper from IEEE. I'm sure you would have an access to IEEE paper module, so you can get that switching
Yeah,
energy,
definitely.
switching energy, time, current, bus voltage. So you look at the results. So results are very, very interesting. I was surprised to see these results on a SiC based devices because these results generally don't come so easily on a SiC based devices.
Because the switching frequency in SiC devices is generally kept high as compared to these SI devices. So due to
Yes,
that reason, such nice waveforms, are very difficult to see. We
yes.
generally
So
get a very huge ringing in this case, and maybe noise as well. So yeah, I agree with your point that these results are really nice.
yeah, so I was also surprised to see VGS. If this picture does not zoom actually, but if we could have zoomed this line at VGS starting, then we could actually measure the Miller plateau also in this. I'm sure we can measure it.
I was able to do that in my research as well, but I had to then hypothetically, ignore those ringing values or noise values, and
Yes,
then I got the approximate values. If we have such kind of perfect values, it will be really nice to get the correct values of this Miller plateau
and
as well as the capacitance.
And see, when we talk in terms, so if you are able to actually characterize the turn on and the turn off in a much better manner, then you can actually reduce your dead time between the switches.
Yeah, correct.
Yeah, yeah, of
And when
course.
you reduce the dead time, the efficiency of the whole switches increases. It becomes much faster. So the efficiency of the whole system increases going forward. So that's what the major idea is all about, sir. Yeah, that's what the major idea all about. Yeah, so if you get into this slide set, just a second. So this ISOView probe, basically, when we talk in this ISOView, there is no electrical path into this probe, and this complete optical path helps you to analyze your signals in a much better way. So you can actually, you don't have any specific uh, inductance which is being created, and there is a lot of ringing and the noise is removed from the whole system. So that's what the idea is all about. And if you look at the CMR ratio of this probe is exceptionally good. In fact, if you look at 100 megahertz, it's if you look at the 100 megahertz, it's actually is a 120 dB. If you look at 10 megahertz, it's actually more than 150 dB. So this is a very very interesting aspect of this ISOV Pro, which is being offered, and you can actually see the high side of the VGS, low side of the VGS, VDS, and low side of the VDS also. So it becomes very easier for you to analyze these type of switches. Okay, going back to our original presentation, right? Yeah, I'll just open up the slide set first. Okay, going back to the first slide, the electric vehicle architecture. Uh, so when we talk in terms of the test and measurement solution, the complete system is defined, as I said in the earlier, it's defined into six applications, key applications. So onboard chargers, AC input, DC input, inverters, motors, battery, DC-DC converters, communication protocols, and the MIMC. So that's where we play. Tektronix plays a very very important role in order to do all of these measurement into a single platform or using different multiple platform in an automated test environments. That's what the complete electric vehicle test system architecture looks like. Okay. Any specific question on that?
Sir,
Yes, please
uh,
go ahead.
with this, is there any provision of thermal analysis of particular device in a simple manner?
So thermal analysis. There is a provision, but it's not available with Tektronix. To be honest, I'll be so there are other organizations who are working. Fluke, I'm sure you must have heard about Fluke. Fluke and Tektronix are one sister concern company. So Fluke has the thermal analyzers which are being used for these thermal analysis of these devices. Tektronix does not have a direct solution to do a thermal analysis.
Okay, sir. And what about the calibration of this device after some time?
Calibration, we have the calibrators which can be used to calibrate these devices. There are calibrators available.
Okay, sir. Thank you.
Yeah. So this whole system. So generally, what people work when we are going into different industries, uh, there are a couple of industries who have segregated their departments into different domains. Somebody might be working on the power electronics part of it. Somebody might be working on the BMS part of it. I'm sure in this group, in this whole forum, there would be people who would be working on the separate divisions. Somebody might be working on the power converters. Somebody might be working on the battery part of it. Somebody might be, because this group does not involve people who are actually building up an electric vehicle. There would be separate people who are working on a separate domains. So when we combine all of these together, then we form one system. That's where Tektronix plays an important role to engage with the industry as well as with the research institutes very closely in different domains. So we have been very closely associated with a lot of IITs. Myself personally associated with IITs, uh, Kanpur or Bombay or Delhi. We have been working on the CAN and SIC devices for automotive applications in power electronics as a new application. So there are a lot of new labs which have been coming in, and we have been involved at different stages. So if anybody has any specific measurement, or if you feel that there is any specific measurement that I have not covered into this small presentation of mine, I'm sure I know this is a small time frame that the presentation slides I could fit in. But if you have any specific measurement that you feel is not covered, then I would be happy to take it with my R&D team also, and we can talk separately on that. Uh, or if you have come across any specific measurement on power electronics, then it would be very great if you can give your feedback, because this is a group of more learned people than me, obviously. So I will be happy to take your feedback on that. Is there anything which you feel is a missed out from the power electronics measurement part of it? Hello. Yeah. So that feedback is definitely most welcome. So what I find most important is how do people do the switching analysis? That's very, very important. How do people do the magnetic analysis of the core? How do we do the inductor losses? How do you understand those losses in a real time situation? How your saturation is happening into the inductors? How your MOSFET is behaving in a real time conditions in the converters? How your motor is actually behaving in different load conditions. Is your motor actually following the standards which are being defined for the motors? Those are like real life situations and the real condition that we actually do and test into this electric vehicle test systems. So Tektronix has a complete solution right from your starting point to the chargers to the EMI EMC. And if you work on any specific domain, I'll be happy to talk separately also, and then I can take a more technical discussions related to it. Yeah, so with that, I'll conclude my discussion here. If somebody has a queries on any specific measurement, and I'll be able to answer it.
સિલેબસ આવે છે સિલેબસ છે 40 પહેલો ને 60% આપણો ટેકનિકલ.
I think somebody's. Yeah. So is there any specific measurement?
Sir,
Yes, sir. Please.
sir, can we use multi-level inverter in the place of VSI?
That is the one of the application that we have been working on, sir. I can't name that IIT, but yes, one of the IITs is working on a multi-level converters into this.
Okay, because
Yeah.
generally when we are talking about inverter, they are saying VSI. Sir, another question is, sir, we are getting from VSI, we are getting the three-level waveform. Sir, harmonics is are there. So how we are eliminating the harmonics in practically? That I'm not getting.
I'm not sure, sir. Sorry. I am not sure. I am majorly into more of a testing side of it. So I think from the designing point of view, I will not be a good person to answer that question.
Okay, sir. Thank you, sir.
I'm sorry for that, but I might not give you a good answer.
Okay, sir.
I'm actually not.
I think I know a bit about this.
Yeah.
I can tell you my experience. We are working on multi-level inverters at Aligarh Muslim University, Aligarh. So that the question that the other fellow has asked, that how we are eliminating the harmonics. See, harmonic elimination in multi-level inverter can be done through various ways. Specifically, you can use certain algorithms which are based on selective harmonic elimination, in which the firing angle has to be adjusted. So there are various algorithms. For example, there is She algorithm, in which you can use any meta-heuristic algorithm also. Other thing is that you can also change the modulation or switching frequency also. So, for example, low frequency, there is one very good technique that is known as NLC. That is people are now using, and we are also using. That is for low frequency, we can also have certain harmonics which are eliminated. And for high frequency, the conventional methods, the PWM, whether it is triangular based or toroidal based or sinusoidal based, then there we can use this particular harmonic elimination, in which this transcendental equations are there, and we have to solve it for alpha 1 and alpha 2 and alpha 3. Various firing angles are solved, and then we have to fire these switches. So lower order harmonics are particularly targeted so that the THD can be reduced. Thank you.
Thank you, sir.
Thank you so much, sir, for that answer. And I have also heard about NFIS, which is a neuro-fuzzy interference system for eliminating the harmonics which are present in a multi-level inverters. So that's also one of the technique which people generally use. It's basically an adaptive neuro-fuzzy interference system. That's also one of the technique which people use for removing harmonics in multi-level inverters. Yes. I'm sure a lot of people work on converters. Any specific question on converters that, from the test and measurement point of view, from the designing point of view or the algorithms, I'm sure I'm not a best person to answer, but yes, from the testing part of it, when it goes actually onto the test system and the parameter measurements, I would be able to answer those questions. Yes. Or from the
Hello,
motor
sir.
side. Yes, yes, ma'am, please.
Actually, we can go for isolation and non-isolation converters, no, sir. What do you suggest that which isolation will be better?
Uh, so, ma'am, you're talking about the measurement part of it or the
Conversion part.
no, I didn't get your question. Can you be a little more specific?
Actually, when a charging station has been to be constructed, we go for DC-DC converters, no, sir. In
Okay.
that, isolation process will be existing and non-isolation process will be existing. That is by using only transformer and the conversion process, and again with the help of power electronic converters.
Right.
Uh, what do you suggest? Better to go with isolation part or with the non-isolation part in order
Isolation. Isolation.
isolation?
Isolation, yes.
If isolation is existing, then EMI and EMC problems will be there, no, sir?
So generally what happens, ma'am, for EMI-EMC, we have to use some shielding method to remove that EMI-EMC issues from the charging part of it. So there are different type of shielding mechanism which are available to remove that EMI-EMC, to eliminate that EMI-EMC part.
Okay. How can we identify that EMI EMC problem, sir?
So, ma'am, so you'll have to use a spectrum analyzer,
Okay.
okay, along with the near field probes. So there is a technique which is known as radiated and a conducted emission. So if you wanted to, so in this case, it would be majorly into the radiated emission. So you'll have to use a spectrum analyzer along with the near field probes to identify those EMI issues. If there is a radiated EMI that is happening across after shielding.
Okay. Thank you, sir.
Yeah.
Just to add, ma'am, one thing I would like to add what Nigam Saab has just said is that if you want to decide whether you go for isolated topology or non-isolated topology, you have to look for the power rating for which you are considering. See, there are various topologies which are transformerless in DC to DC converters. They don't use any transformer. They use inductors or they use coupled inductors to get very high gain. If you are talking about high gain DC to DC converters, whatever you are telling that the use of transformer, the transformer is certainly used in certain situations in which very high efficiency is needed and very high voltage at the secondary side is needed and for very high power rating. So in that situation, this non-isolated and not a common ground configuration doesn't work well because we have seen in our experiments and we have observed it in our lab also that the efficiency of these non-isolated converters without transformer fall very steeply at higher duty ratio because of the parasitic resistances. So that's why you need this transformer at some point of time. However, if your power rating is small, for example, 200 watts, 300 watts, not in kilowatts, okay, then you can use this non-isolated configuration in which there is no voltage gain is good, but there is no transformer in between. So each of these configurations have merits as well as demerits. And there is a very good paper, a review paper on step up high gain DC to DC topologies by Firoz Shah. There is an Iranian group working on this high gain DC to DC topology. So if you just go on IEEE Explore and write down the review on high gain DC to DC topology, it's a very highly cited and very beautifully written paper. And in all these pros and cons of different topologies have been discussed. Thank you.
Okay, sir. Thank you so much. Sir, can you please share that paper title, no? So that I can go through that
Okay,
one.
I will share on the group.
Okay, thank you, sir. Your good name, sir?
My name is Mohammad Zaid. I'm presently working as assistant professor in Aligarh Muslim University, Aligarh, UP.
Okay, okay. Thank you so much, sir. It was
Thank.
based upon voltage, we decide which one will be better.
Yeah, there are so many parameters, but voltage and power rating are important ones.
Okay, okay. Thank you so much once again.
Thank you so much, sir. That was really insightful. Yeah. So, torque developed by the motor is has any impact which is the AC created by the inverter? Hello. Yes.
Nitin sir, so I think are you done with the session as such?
Yeah, I'm done. I'm done with the presentation, and the we had good technical questions also, and thanks to few of the team members in this group for helping me out with the questionnaires which few of the team members asked. So I'm just popping up my slide set just for a minute.
Mhm. Yes. So participants, I hope if you don't have
So
any other questions, yeah.
so we can just get connected on LinkedIn if you feel like, and if you wanted to have some more detailed discussions or some specific sessions on the test and measurement side by Tektronix on specific converters, battery management, or EMI/EMC, just get me connected. I'll be happy to do that session, especially for your team. Because in this session we were majorly talking on the top level architectures and the measurement part of it, but if you wanted to see a real measurement and how do we exactly do it, I didn't have, we have few of these setups available in the office, but since we are not traveling right now, but going forward, if you feel to have a real gallium nitride and SiC based measurement, then we have a setup available in Bangalore, and I can call that setup to show you the some real live measurements on the GAN devices, or if you wanted to see something on a communication or EMI/EMC or AC charging station measurements. So just get me connected, and I'll be happy to show you some live sessions.
Yeah, actually, Nitin,
Yes.
sir, I had already requested Jatan sir to do that
Okay.
because initially this session was scheduled for the same thing, so that participants can view a live demo of that, as you said. But
Oh,
due to some health issues with Jatan sir's family and all, yeah, we had to reschedule the talk with you. So
actually, sir,
otherwise,
what
he was
happens?
doing it actually mostly from Bangalore.
I tried to get the probes from Bangalore to Delhi, but due to lockdown, I our logistics were not working. So otherwise, I would have set up actual measurement on a
Mhm.
GAN device today. But due to lockdown, I could not get the instrument and the probes and the setups at my home. And unfortunately, we had to go only through the presentation. Otherwise, this session I wanted to keep a real live demo also. But
Yeah.
not a worry, sir. Going forward, if whenever you feel like, maybe in the since the lockdown is open, we can get the instruments and then we can do this.
Yeah, you can, sir. What we can do is, you can, once it is done, what you can do is you can share me a video of those measurements with some explanation and all. And what I can do is I'll share that video with all the participants, and I'll again, try to join it with your this session and upload it on the Atal website as well.
Oh, okay, perfect, sir. Yeah,
So you can,
makes sense.
you just send me that video as soon as possible. Maybe your or maybe from Bangalore if someone is able to do that. That's fine.
Sure, sir.
So you
I'll share
can
that video.
share it with all the participants as well.
Sure, sir. I'll share that video, sir.
Yeah, I think that will be a good option. Right?
Perfect. Uh, Thank you so much from the GC Valsad team for inviting me for this session, and it was a good learning, a good session, interactive session. and I hope to get connected with the team members very soon on a different platforms. So with
Yeah,
that, I will
definitely, sir. I again, thank you from the Electrical Engineering Department, GEC Valsad, and our team for taking out your time and delivering such a nice session. It was really, a very interesting session as the participants and we all came to, know about all those instruments, the testing measurements and all. And this silicon, this gallium nitride and silicon carbide devices introduction was a really nice part in your session because actually I was personally thinking of arranging one session regarding wide bandgap devices as my own research interest is also there in this case. But anyways, I couldn't. But your presentation included that thing, so it was really nice as of that. So I again thank you very much, Nitin sir, and I hope everyone will get connected to you. And
Wani sir, there is one query that I would like to ask.
yes, sir. Please go ahead.
How do you plan to conduct the test which you have announced yesterday? Is it will be on a quiz type or objective type? What will be the format?
I'll be going on that, sir. Please wait. Actually, just let me free the speaker first. Okay, so
Okay.
that I can discuss that thing. Actually, I was coming to that only. Right. So, Nitin sir, I again thank you. So, if you are done, like you can leave the meeting, no problem.
sure, sir. Thank you so
Yeah.
much, and have a good day and be safe, everyone. Bye bye.
Yeah. Sir, please share your PPT to me so that I
Yeah,
can.
I'll share it. I'll
Please
share
share.
it.
I-
Thank you so much. Have a good day, everyone. Bye bye.
Yeah, thank you. Yeah, so participants, two things. One is, first of all, I'd like to inform you all. Just a second. Yeah, so I'd like to inform you two things. The first is that